Next on our study of trigonometric functions, we want to take a look at the graph of cosecant of x and the graph of secant of x. We know that cosecant of x is, let me get my drawing pen here. Let me actually, how does that look? I'm going to make it a little bit darker. A little bit thicker here. And we'll switch to black. Okay. So if I'm looking at like y equals cosecant of x, oops, my c got confused with a parenthesis. I know that that is 1 over the sine of x. And so what I've got here is a graph of the sine function. And I want to add to that the graph of the cosecant function. We're looking here at about pi. This maximum occurs at pi over 2. Here is our 3 pi over 2 is about 5. And 2 pi, and we can continue on. This would be another pi over 2 past that. So 5 pi over 2. And 3 pi is here. And we'll throw in a couple negative values as well. Negative pi over 2. This peak is at a negative 3 pi over 2. This minimum down here, this bottom of the wave, is at a negative 5 pi over 2. So that's our sine function. What I want to look at is the cosecant function, which is 1 over the sine of x. Well, I know that here at 1, when x is equal to, well, when the y value is 1, when the sine is equal to 1, 1 over 1 is just 1. So at pi over 2, the cosecant function is going to have a value at 1. As I move sort of from that point to the left, the sine value gets smaller and smaller and smaller. And if you look at, say, if you have like the sine of x is equal to 1/10, then the cosecant of x would equal 10. So when the y value is down here at 1/10, I know that the cosecant value would be 10. And if the sine of x is equal to 1/100th, then the cosecant of x would equal 100. The cosecant would equal 100. And so as I get really close to 0 here, what I end up with is really, really large values. And my cosecant is going to have a vertical asymptote. It's going to come down here, going to hit that 1 value. And then right at pi over 2, I've got sort of that same behavior. My values get smaller and smaller for the sine function. So the reciprocal ends up getting larger and larger. And I have a vertical asymptote at pi over 2 there, at pi, where the sine function is equal to 0. And that's going to happen throughout this place. Every place the sine function is equal to 0, I'm going to have a vertical asymptote. At this 3 pi over 2, which is a little bit smaller than 5 in here, I'm going to have a y value of 1. You get a y value there of 1. Come here. Why aren't you drawing? Oh, because I'm holding it too long. It's not registering. Going to get a y value there of 1. And then as I'm in here next to pi over 2, the y value is going to be very large again, but negative for cosecant. Sine is going to be very small, but cosecant is going to be very large. And so I get another sort of U-shaped graph that ends up in there where I have 2 asymptotes. But everything on this side is below the x-axis because the sine function itself is negative. When the sine function turns positive, I end up with another one of these U-shaped things happening there. And if we go to the negative side, we also have a negative asymptote at a vertical asymptote at negative pi over 2, and I'm going to be down here below the x-axis for my cosecant graph would be in there like that. And I've got an asymptote right along the x-axis as well. And so we end up with these repeating periodic sort of graphs. It's not the wave that we get like with the sine, but it's sort of it's kind of a reciprocal of a wave. In there, we get these sort of U-shaped sort of things that happen throughout there, being the reciprocal of that. The period for the cosecant graph is the same sort of thing. If I go from like valley to valley, I'm going from pi over 2 to 5 pi over 2. So that's a difference of 4 pi over 2, or 2 pi. The period for the cosecant is also 2 pi. Just like sine, the period is going to be 2 pi. The domain, the sine function is defined everywhere, and the cosecant is defined all real numbers except these places where the sine value is 0. So it's going to happen at it's going to happen over here at minus 2 pi, minus pi, 0 pi, 2 pi, 3 pi, 4 pi, 5 pi. All of those values, the sine value is going to be undefined. So we can say that as pi k, where k is any integer. So the period is 2 pi, but the looping nature of this is that we end up with, it's 2 pi before you get back to repeating again in there, but every pi units you get to another place where there's an asymptote. They're 180 degrees apart. Every place where the sine function is 0, you're going to get that. The range is a little bit more complicated. Well, actually, the range maybe isn't a little more complicated. The lowest this graph ever goes, well, you've got a negative infinity down here. The graph has vertical asymptotes that go from negative infinity, but it stops at 1. It goes all the way up to 1. It actually hits -1. Should be -1 in there. I said 1, but it should be -1. And then there's this gap, and it picks up again at 1 and then goes to positive infinity. So the range is from negative infinity to -1. Added to that, you have 1 to infinity, but you've got a gap between -1 and 1 where the cosecant function is not defined. All right, cosecant function is the reciprocal of the sine function. And if I come down here and look at the cosine function, here's our y equals cosine of x. And if I want to graph the secant of x, I'm going to have the same sort of behavior happening. I'm going to have vertical asymptotes. Actually, let me grab that graph. Let me make that graph bigger, give us something bigger to work with. And now I've got some extra little bits I want to erase. Okay, back to drawing. Okay, back to drawing here. I've got vertical asymptotes wherever the cosine now is equal to 0. This is the cosine curve. Cosine curve always starts at a maximum on the y-axis there. So if I'm looking at drawing in the cosine of x, but I want to add in secant of x, we got vertical asymptotes wherever cosine is equal to 0, whole series of them there. And we get that same at 0, we know that the cosine is equal to 1, and we know that secant of x is 1 over cosine of x. So 1 divided by 1 would be 1. So we're going to get a y value there of 1. I keep getting that select thing instead of if I hold my pen down, it selects, but I don't want to select. I just want to draw. And then I end up with that same sort of U-shaped graph that I saw with cosecant in there, where I come across and I have these U-shaped things because I have vertical asymptotes. As we get close to here, pi over 2 on the x-axis, the cosine is going to be 0, but I get small positive values on the left side of it, small negative values for the cosine, and so the 1 over that small negative gives you a really large value in there. So I get a vertical asymptote at pi over 2. Pi, we have a value of -1. 3 pi over 2, I've got a vertical asymptote. And 2 pi, I'm back to having a y value of 1. And so if you look at the period, the distance from peak to peak, it's going to be the same, or sort of the, well, I guess this is kind of the peak on this side. The peaks are at negative values. The peak to peak there, that's the difference of 2 pi. The period is also 2 pi in there. The domain is all real numbers, except you've got this at pi over 2 and 3 pi over 2, and this point out here is going to actually be 5 pi over 2, and you've got minus pi over 2, and so we describe those as saying pi over 2 plus k times pi, plus some constant times pi in there, where k is an element of the integers. So if k is equal to -1, I'm going to get pi over 2 minus pi, which is going to give you the negative pi over 2 here. If I get pi over 2 plus pi over 2 plus pi, 2 pi over 2 pi, or 2 pi over 2 would be 3 pi over 2. Anyway, so that's the domain in there. Range is the same as the cosecant, -infinity up to -1, and from 1 to infinity there for the range on the cosine. So secant is 1 over cosine, has a graph where you've got a u, and you're starting that u at the, or if you look at the origin at the x-intercept, you're starting at the bottom of one of those u's. As opposed to the cosecant, we have an asymptote right at 0, and then the peak is a little bit farther over. Okay, let's go play around with some sliders here. Oh, that was me exporting my graph. Let's look at the cosecant graph and the slider sort of things. I've got the sine graph in blue as a reference, but if I make that a value there stretches things. They both, notice both halves are moving away from the x-axis out there. If I move a to, let's see, we're about 3 there. It looks like my height that I'm dealing with is 3 units here. I've got a 3-unit value here from the origin up, or from the origin down. It's a 3-unit dip in there. And if I make that a value larger, it gets even larger. If I go to, I'm about 5. Sort of my amplitude is 5. It's a total of 10-unit spread from peak to peak, from bottom here. If you looked at the distance from this distance from that peak all the way down to this bottom sort of thing, from sort of where do these peaks line up and where do they end. When a is equal to 5, I'm getting a total of a 10-unit spread. It's 5 up and 5 down from there. In there. Okay, so that's what A does. Changes that vertical spacing again, spreads them out farther apart, pushes them away from the x-axis when A is positive. Let's go when A goes down closer to 0. Here we are at 1, and then as I make A, actually let me clear off all my drawings. As I make A closer to 0, we see it flattens out. It gets closer and closer and closer to that x-axis. Right at 0, it actually equals the x-axis, because then we're looking at just y equals 0. We're not looking at a cosecant function at all. But as we go to negative, did you see that the graph kind of flips over that x-axis? It flips over the x-axis and kind of does that same sort of thing. As a gets larger in absolute value, you move farther and farther away from that x-axis there. So it's a reflection when you turn negative over the x-axis. We'll go back to a equals 1 There's A equals 1. B, what does B do? Well, B adjusts the period again. As B gets larger, the period gets smaller and smaller and smaller. So if I take B equal to 3, my period would be right about 2. It's actually, the period is going to be 2 pi divided by 3. So 2 pi divided by 3 is pretty close to 3. It's almost, since pi is about 3, it's almost 6 divided by 3, but we're not quite at 2. It's a little bit to the left of 2 there, a little bit farther to the right of 2, sorry, there for our period. And so 2 pi divided by B gives you the period. As B gets larger, the period gets smaller. As B gets smaller, the period gets larger. And then when you go to negative, it's kind of hard to see it there, but it flips over the y-axis. With the negative y values, it flips over the y-axis in there. All right, let's go back to B equals 1. C is, moves the graph horizontally. Notice when I move the slider to the right, if I make C in the positive direction, the graph actually seems to shift in the negative direction. And when I move C in the negative direction, the graph shifts to the positive direction in there. So if I look, C equals -2, if I look at where my red dot was here, that's about 1 and 3 spots. And my green dot is 1 and 3 spots. It shifted over a total of 2 units from the red dot to the green dot. It's a shift of 3 units in there. Oh no, shift of 2 units, sorry. Shift of 2 units. 1 to 3 is a difference of 2. So it shifted 2 units to the right there when C is equal to 2. Let's make that C back down to 0. And these should be the exact same. I mean, the graph is different, but the transformations are roughly the same. If you make D bigger, the graph shifts up. Note this is different than the shift that we saw when we changed A. When we shift D, both the top and the bottom are moving up. Sort of the gap between those two is staying the same. The gap does not increase between the peaks and the valleys there. But when I change A, both they get farther away from the x-axis. One moves up and one moves down in there when you change A. One part is moving up, one is moving down, moving away from the x-axis in there. Let's see, I want A to be 1 again. There's A equals 1. And if I move D to 2 or 3, D is 3. If you look at the difference here, my y point here with the red dot was at y equals 1. And now my y value is up here at y equals 4. I've got an increase of 4 units there. I went from -1. If I go, I should maybe point to where I'm looking. If I go over here at this point, I'm going from a value of -1 to a value of +2. So that difference has been shifted up 3. And this point has been shifted up 3 there when my D value is 3. Okay. We can also play the mystery game of trying to match the mystery graph. If we've got a graph, we want to maybe match it to the graph. So let's jump over to my mystery graph here. And quick hide it before we saw it there. Maybe you can pause and see what that is. But my goal here is to find out what's the equation for this graph. It's either a cotangent or a cosecant or secant. I've got those U shapes with the vertical asymptotes in there. And so I'm not sure. We can do a couple of things to look at where the period is. It looks like our numbers are looking out pretty nice here. That if I go from this point to this point, that is a distance of how far from this peak to that peak. It looks like I'm going from a quarter. So if that's a half, then we're halfway between those. That's a quarter to 2 1/4, 2 1/4. So that's a difference of 2. So I've got a period. It looks like the period here is 2. The amplitude, or the A value, is going to be our vertical stretch. And so if I'm looking for what's the difference from where this peak is at 4 to where my peak is down here at -2, I see that that's a total distance of from -2 to 4 is 6. And so if I split that in half, the midline is going to be right here at 1. And from that 1, I'm going up 3 and down 3. So the midline that I'm looking at there is going to be 3. So for whatever graph I'm looking at, I know it's going to be y equals 3. And then we've got a choice of either using the cosecant or secant. I'm going to start with cosecant. And then it's been shifted up 1. I know it's got a +1. The midline is up 1 in there. Those values are going to be the same whether you're using a secant or a cosecant. Those values are going to be the same. And actually, the b value is going to be the same as well. I know the period here, it looks like it's going to be 2. And so 2 pi divided by b has to equal my period of 2. And so 2 pi equals 2b. And you can solve for b by dividing both sides by 2. And we get b is equal to pi. So it's going to be pi x in both of those. And then the last thing I need to deal with is some sort of horizontal shift. And this graph is shifted a little bit. We have to decide whether we want to use a secant or a cosecant. And I'm actually going to do both because it's gonna matter there. Let me kind of clean up some of this stuff. Whoops, I missed the eraser. There's the eraser. Clean up some of this things. So if we remember what the cosecant looked like, the cosecant graph, I'm going to jump back to it here. Whoops, I need my pointer instead of my eraser. The cosecant graph has an asymptote right along the y-axis here. And the cosine graph starts at one of the minimums, at the dip of this upper U. And so what I want to go back to is I want to go back and look at what have I got there. If I'm looking for a cosecant, I want to look for an asymptote. In particular, an asymptote between an upper branch and a lower branch. So it looks like there's an asymptote right about here. It looks like I've got a vertical asymptote right about there. And so if I were to shift this graph over, well, it's like it's a sine function or a cosecant function that's been shifted left by that much, by a little bit here. And unfortunately, it doesn't flop right in exactly. You don't put the 0.25 or the 1/4 in directly, well, -1/4, -0.25. The nice way that I like to do that is I like to take that bx plus c and set it equal to 0. That will kind of help us identify our shift. What value in my new graph corresponds to 0? And in my new graph, corresponding to 0 on the cosecant, where this asymptote was, it's -1/4. So, or -1/4 in there. So I'm going to put -1/4 in for x. B I know is pi. And I want to find out what that c would be. So c would be, I want to solve for c. So -pi/4 plus c equals 0. So c is equal to pi/4. So with the cosecant graph, I want a plus pi/4. So I'm not putting in the -1/4. I actually have to do a little bit of calculation over here on the side to figure out what I want to put in for the cosecant. So it's 3 cosecant pi x plus pi/4, and then +1 to shift everything up 1 in there. So the vertical stuff is pretty nice. The shift and the stretch, the amplitude and the +1, those go in just exactly like you'd expect them to. All right, now what if I wanted to do a secant graph instead? Let me change my ink color here because I'm going to work with the secant graph. If we recall that what the secant graph looked like, the secant graph Here's the bottom one. Oh, I got all my work copied over, but there's a secant graph. It's starting at one of these minimums here. So if I go back to Desmos, there's the Desmos thing. If I'm looking at secant, I want to look at one of these minimums as my starting point. I want to look at like this point here, one of these minimums as my starting point. And so the X value corresponding to that, it looks like it's positive 1/4. And so I want to take that bx plus c for the secant graph. I'm going to use positive 1/4. B value stays pi plus c equals 0. So instead of starting at 0, my graph is starting at 1/4. So I want to find what's the new x that corresponds to a 0 in there is what I'm doing. And if I solve that, we'll find that c is equal to minus 1/4. If my c value is negative 1/4 pi, I'll get the cosecant graph in there to match up. That will shift the graph over just enough so that the minimum is at that point. So you can think of it as either a secant or a cosecant. It's been shifted just a little. It doesn't matter which one you use. They both actually produce the same graph. And if I go over here and look at my graph, let's show me your graphs equations again. We'll see that I'm graphing the exact same equation twice. Y equals 3 cosecant of pi x plus pi over 4 plus 1. So it's the cosecant graph with the plus pi over 4 to shift it actually in the negative direction, pi over 4 units. And then the secant was the one with the minus pi over 4 in there. That kind of distorted my window a little bit, so my markings don't quite line up like they used to. But that's how we can find a minimum and what our cosecant and secant graphs look like.